Most engineers make this mistake. They select a material based on tensile strength and assume the job is done. But in real engineering, that's exactly how failures begin. The strongest material is often not the best material. In fact, choosing a higher strength alloy without understanding the actual working conditions can reduce component life instead of improving it. So how do real engineers select materials? The answer lies not in strength alone, but in understanding failure. Material selection always starts with a simple but powerful question. How will this part fail? Will it deform under load, crack due to fatigue, wear out due to surface interaction, or degrade due to environmental exposure? Take an excavator bucket pin as an example. It doesn't fail because it's weak in tension. It fails due to repeated cyclic loading, impact shocks, and surface wear. If you only optimize for strength in such a case, you are solving the wrong problem. Real engineering is about predicting failure modes and designing against them. Once you clearly understand how a component is going to fail, the next level of decision-making moves into material science, specifically the relationship between composition, microstructure, and resulting properties. This is where many engineers stop too early by only looking at the chemical composition table, but in reality, composition is just the starting point. What truly governs performance is how that composition transforms into a specific microstructure through processing. At the composition level, each alloying element plays a targeted role in modifying the behavior of iron. Carbon is the most influential element. It increases hardness and strength by enabling the formation of martensite, but at the cost of ductility and toughness. Chromium improves hardenability, meaning it allows thicker sections to transform into harder phases during heat treatment, and it also contributes to corrosion resistance by forming stable oxides. Molybdenum enhances strength at elevated temperatures and reduces the risk of temper embrittlement, which is critical in dynamically loaded components. Nickel, on the other hand, is one of the most effective elements for improving toughness, especially at low temperatures, making materials more resistant to brittle fracture. Manganese and silicon also play supporting roles by improving strength, deoxidation, and overall stability of the steel. However, composition alone does not determine performance. Two steels with similar compositions can behave completely differently depending on how they are processed. This is where microstructure becomes the controlling factor. Microstructure refers to the internal arrangement of phases within the material, and it is primarily controlled through heat treatment. For example, a slowly cooled steel forms ferrite and pearlite, which provide good ductility but limited strength. Faster cooling can produce bainite, which offers a superior balance of strength and toughness. Extremely rapid cooling, such as quenching, produces martensite, which is very hard and strong but also brittle if not tempered properly. This is why heat treatment is not just an optional step, it is a design variable. By controlling heating temperature, cooling rate, and tempering conditions, engineers can tune the microstructure to match the exact performance requirements of the component. The same base material can be optimized for wear resistance, fatigue strength, or impact toughness simply by altering its microstructure. A very practical example of this concept is 20MnNCr5. In its untreated state, it is relatively soft and not particularly useful for high-performance applications. However, when subjected to carburizing followed by quenching and tempering, it develops a dual microstructure, a high-carbon martensitic surface layer that provides excellent wear resistance, and a low-carbon tougher core that can absorb shock and resist crack propagation. This combination makes it ideal for gears and contact-heavy components where both surface durability and core toughness are essential. In contrast, 25CrMO4 is typically used in a quenched and tempered condition to produce a uniform tempered martensitic or bainitic structure throughout the cross-section. This results in a well-balanced combination of strength, fatigue resistance and toughness, making it suitable for shafts, bolts, and structural components subjected to cyclic and dynamic loads. Unlike case-hardening steels, it does not rely on a hard surface layer but instead provides consistent mechanical properties across the entire section. One of the most persistent misconceptions in engineering is the tendency to judge a material primarily by its yield strength or ultimate tensile strength, UTS. These numbers are easy to compare, prominently displayed in data sheets, and often give a false sense of confidence. However, they represent performance under idealized monotonic loading conditions, essentially a one-time, steadily increasing load until deformation or failure. Real components almost never operate this way. In actual service conditions, especially in heavy machinery, automotive systems and rotating equipment, components are subjected to cyclic, fluctuating and multi-axial stresses. This is where fatigue strength becomes far more relevant than static strength. A material with very high tensile strength can still fail at stress levels well below its yield strength if those stresses are applied repeatedly over time. This phenomenon is governed by SN behavior, stress versus number of cycles, and many high-strength steels actually exhibit a steeper fatigue curve, meaning they are more sensitive to small increases in stress amplitude. Closely related to fatigue is fracture toughness, which defines a material's ability to resist crack initiation and, more importantly, crack propagation. In real components, microscopic defects, inclusions, machining marks, or surface damage act as stress concentrators. Once a crack initiates, the material's fracture toughness determines whether that crack will grow slowly and safely, or propagate suddenly and catastrophically. High-strength materials, particularly those with high hardness, often have lower fracture toughness, making them more vulnerable to brittle failure. Another critical but often overlooked factor is notch sensitivity. In theory, stress calculations assume smooth, ideal geometries. In reality, every component has geometric discontinuities, keyways, threads, fillets, oil holes, or even surface roughness. These features create localized stress concentrations. High-strength steels tend to be more notch-sensitive, meaning their fatigue performance drops significantly in the presence of such discontinuities. In contrast, slightly lower strength but tougher materials can better redistribute stresses and tolerate imperfections. This brings us to a very common industry example, AISI 4140. It is widely used because it offers a good balance of strength, hardenability, and availability. In many cases, it performs reliably when properly heat-treated. However, it is often overused as a default choice, especially in applications involving high cyclic loads or severe surface interactions. Engineers may select 4140 for its tensile strength without fully accounting for fatigue loading, surface finish, or stress concentrations. As a result, components like shafts, pins, or bolts made from 4140 can experience premature fatigue failure if not carefully designed and processed. For example, in a rotating shaft with a keyway, the local stress at the keyway root can be several times higher than the nominal stress. If the material is high strength but notch sensitive, a fatigue crack can initiate at that location and propagate over time, eventually leading to sudden failure, even though the applied stress is well below the yield strength. In such cases, a material with slightly lower strength but higher toughness and better fatigue resistance, or a properly surface-treated version, may perform significantly better. Environmental conditions add another layer of complexity. A material that performs perfectly in a controlled lab environment can fail rapidly in real-world conditions. Exposure to moisture, chemicals, or temperature extremes can drastically change material behavior. Chloride-rich environments can cause pitting corrosion, while low temperatures can lead to brittle fracture in steels that are not adequately toughened. At high temperatures, creep becomes a dominant failure mechanism. Ignoring environmental effects during material selection is one of the fastest ways to guarantee failure in the field. Wear is another critical factor that is often misunderstood. Many engineers assume that increasing hardness automatically improves wear resistance, but this is only partially true. A very hard material can resist abrasion, but if it lacks toughness, it may crack or spall under impact loading. The most effective solution is often a combination of a hard surface and a tough core. This is why case-hardening steels are widely used in gears and heavily loaded contact components. They provide a wear-resistant surface while maintaining structural integrity beneath. Heat treatment is the hidden lever that ties everything together. It is not just the material grade that defines performance, but how that material is processed. Techniques such as carburizing, nitriding, and quenching and tempering can dramatically alter hardness, strength, and fatigue resistance. The same base material, when heat-treated differently, can exhibit completely different behavior in service. This is why experienced engineers always consider material and heat treatment as a combined system, rather than separate decisions. Of course, real-world engineering is not just about performance, it is also about manufacturability and cost. A material may meet all technical requirements, but still be impractical if it is difficult to machine, weld, or source. For instance, while AISI 4140 offers excellent strength, its weldability is limited compared to lower carbon steels. Every material choice involves trade-offs, and understanding these trade-offs is what separates good engineers from great ones. Finally, cost must always be evaluated in terms of the entire life cycle, not just the raw material price. Choosing a cheaper material might reduce initial cost, but if it leads to higher wear, frequent maintenance, or unexpected failures, the overall cost increases significantly. The goal is not to minimize material cost, but to optimize total system cost over the component's life. In real engineering applications, the selection becomes clearer when you align material properties with functional requirements. For example, gears require high surface hardness and fatigue resistance, making case-hardening steels like 20-menonon CR5 an ideal choice. Shafts, on the other hand, need to withstand torsion and cyclic loading, which is why alloy steels like 25CRMO4 are commonly used. At the end of the day, the best material is not the strongest, hardest, or most expensive. It is the one that survives the longest under real operating conditions while minimizing total cost. That is the mindset of a true engineer, designing not just for performance, but for reliability, efficiency, and durability in the real world. If you want to design like real heavy machinery engineers, start thinking beyond strength and start thinking in terms of failure, environment, and life cycle. Subscribe to Design Hub Heavy Machinery for deep engineering insights, and in the next video we'll break down how to calculate exact material requirements for real components.